Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, we'll look at examining specific model components in multiple regression. So the overall F-test tells us whether there's an overall effect of the entire set of predictor variables on the outcome. And so a significant F-test implies that the population R squared does not equal 0, but it doesn't tell us which predictor variables are influencing the outcome significantly. We have to do additional tests to figure out which predictors are significantly influencing the outcome. So this is where the slope coefficients come in. Each slope coefficient reflects the unique influence of that predictor variable above and beyond all the other predictor variables. A way to think about this is if we think of variation in each variable as a circle and we create a Venn diagram with those circles. So in our smoking example, we have the cigarettes outcome and we have stress and years smoking as predictors. Where the scores co-vary is where the Venn diagrams overlap. So where the Venn diagrams overlap between cigarettes and stress is the representation, represents the slope coefficient for stress on the smoking outcome, and the same for years smoking. And I've highlighted these in this figure to show you. So to conduct significance testing for each specific component or for each predictor, we want to know the unique contribution of each predictor. And so we test with the hypotheses whether the slope coefficients are equal to 0. So whether beta in the population is equal to 0, which would be the null hypothesis, or whether beta in the population is not equal to 0, which would be the alternative hypothesis. And for the purposes of the specific predictor variables influence, we'll use the t-statistic for significance testing. So another way to think about this is that we have a unique t-test for each predictor in the model, because we're relating that unique influence of that predictor on the outcome. So we have a t-statistic for the estimated B1 coefficient and a t-statistic for the estimated B2 coefficient. To calculate the t-statistics, we simply take the estimate of the slope coefficient and divide it by the standard error of that coefficient. And we can get this in SPSS. So when we use this t-statistic, essentially, we are interested in the difference between the sample and the population estimates. And what we do is plug in the hypothesized population slope under the null hypothesis. So t reduces to the estimated slope coefficient over the standard error, which is the sampling error of the slope, because the hypothesized population slope under the null hypothesis is 0. So as an example, let's take the predictor of years smoking and look at the coefficient for years smoking relating to the smoking intensity outcome. The value of the years smoking coefficient was 0.65. So, and the standard error of the coefficient was 0.35. So to calculate the t-statistic, we would subtract 0, or the expected population coefficient size under the null hypothesis, from 0.65 and divide by 0.35, which would give us a t-statistic of 1.85. Now, we interpret this t-statistic as follows. The difference between the estimate and the hypothesis, the null hypothesis, is 1.85 times larger than the expected difference due to sampling error alone. Here is where we find that information in the SPSS output. So you can see the size of the coefficients, and it's the unstandardized coefficients that are used in the calculation of t. And we can see how those are calculated. And for each t statistic, there's a corresponding p-value that SPSS will automatically give you. So if we look at the t-statistic for the stress variable, it's 2.845, and the corresponding p-value is 0.015. So stress is significantly influencing smoking intensity, or stress significantly predicts smoking intensity. The t-statistic, which I just showed the calculation for, relating years smoking to the smoking intensity outcome, is 1.853. And it's not significant because the p-value is 0.089. So if p is not less than 0.05, if it's greater than 0.05, then that's not a significant predictor. So in conclusion, if we take all of the results together from the full model and looking at the specific components, we would say overall that the set of predictors did account for significant variation in smoking intensity behavior. When then we probe the specific components and look at the tests for those, we would say that the influence of stress was significant, but years smoking added no unique explanatory power above and beyond stress. Now let's talk for a minute about standardized coefficients. The slope coefficients here are not comparable because our predictor variables have different scales. So we talked a little bit about standardized coefficients with linear regression. What we want to do is convert all of our variables to z-scores, both predictors and the outcomes, outcome, so that we can compare the coefficients to one another. This puts all slope coefficients in standard deviation units, and so we can compare these coefficients to one another in terms of absolute sizes. Now I've highlighted here where to find those in the SPSS output. So the standardized coefficient of stress is 0.576, and the standardized coefficient of years smoking is 0.375. And here's how we would interpret those coefficients. We would say, because as we talked about in one of the first lectures on multiple regression, we are always controlling for or accounting for the other predictor. So for number of years smoking as a predictor, we would say that controlling for stress, the other predictor, a 1 standard deviation increase in years of smoking increases the number of cigarettes smoked by 0.375 standard deviations. For the stress predictor, we would say that controlling for years smoking, a 1 standard deviation increase in stress increases the number of cigarettes smoked by 0.576 standard deviations. We can directly compare the sizes of these coefficients because we are always talking about standard deviation units when we are using standardized coefficients. So we can actually compare the magnitude, and when we do, we see that the magnitude of the stress effect is greater, which is what we would expect to see because stress was the only significant predictor in the model. This concludes the series of lectures on multiple regression. In the next lectures, I'll describe other regression models such as models with moderators and models with mediators.